Nuclear physicists model nuclear fission and fusion with exponential functions. They also use the inverse of exponential functions, which in mathematics is the logarithmic function. Hi, my name is Tom Atwater, and in today's lesson, we will investigate the derivatives of both of these functions. Let's start off with a formula. The derivative of e to the x. The derivative of e to the x is e to the x. Yes, that's right. The derivative of e to the x is itself. If u is a differentiable function of x, then if you have the derivative of e raised to the power u, then again you get that the derivative is e to the u, but we also have to find the derivative of u. So it's e to the u times du dx. Let's try this out on a couple of examples. We have y equals e raised to the 2x over 3. So first, we know that the derivative of e to the x, whatever that x may be, is e to the x. So y prime is going to be equal to e to the 2x over 3. But then what we need to do is take the derivative of this function. And the derivative of 2x over 3 is simply equal to 2/3. So the derivative of y equals e raised to the 2x over 3 is 2/3 e raised to the 2x over 3. Let's look at y equals the e raised to the square root of x. Well, again, y prime will be equal to e raised to the square root of x. But again, we have to take the derivative of the square root function. And that's equal to 1/2 square roots of x. So that will be our derivative for y equals e raised to the square root of x. Now, let's take a look at the derivative of a function which is y equals a raised to the x. So the derivative of y equals a raised to the function u, for a being greater than 0 and a not equaling 1, then the derivative of a raised to the power u is equal to a to the u times the log of a times the derivative du dx. Let's work this example so you can see that particular rule in action. So we want to take y prime, and y prime is going to be equal to that function 3 raised to the cosecant of x times the natural logarithm of 3, and then we have to take the derivative of cosecant, the exponent. And the derivative of cosecant is negative cosecant x times cotan of x. So there's a fairly complicated looking derivative, but an easy application of that particular rule. Now what I'd like to do is take a look at the derivative of the natural logarithm. If u is a differentiable function of x and u is greater than 0, then the derivative of log u, the natural log of u, is equal to 1/u times the derivative of u, du dx. If the base of the logarithm has any other base than e, the rule is slightly different. So let's take a look at that particular case. If we have the derivative of y equals log base a of u, well, if u is differentiable function of x and u is greater than 0, and for a greater than 0 but not equal to 1, then the derivative of log base a of u is equal to 1/u times the log of a times the derivative du dx. Once again, for illustration, let's do some examples so you can see how to apply this formula. let's take the examples y equals log of x squared. Then y equals the log of log x. And y equals log base 2 of 1 over x. Let me get a little bit more space here and now apply that particular rule to these three functions. So this is going to be y prime will be equal to 1 over x squared times the natural log of e times that derivative 2x. Now, the natural log of e is just equal to 1. We can cancel that x with one of these, and so the result here is the answer 2 over x. Let's do the second example, y equals the natural log of the natural log of x. So y prime will be equal to 1 over the natural log of x times the natural log of e times 1 over x, because we have to take the derivative of natural log of x. So again, the natural log of e would make this is 1, so this derivative will be equal to 1 over x times the natural log of x. So that's our derivative of log x. So now let's do the problem log base 2 of 1 over x. But I'm going to clear this screen to give me a little bit more space. And so we have this log base 2 of 1 over x, and that's the second rule that we're going to apply. So y prime for this is going to be equal to 1 over x times the natural log of 2. And then we have to multiply that by the derivative of this, which is going to be -1 over x squared. And when we simplify this, it'll work out to be -1 over x times the natural log of 2. And again, note that that means x is greater than 0. So that's an application of those two rules. Now, we're going to look at one other technique for differentiating called logarithmic differentiation. This technique is useful when the function that you need to differentiate has a variable base as well as a variable exponent. In this situation, we will take the logarithm of both sides and apply any of the log properties and then differentiate implicitly. So let's take a look at the example. Use the technique of logarithmic differentiation to find the derivative dy dx. And the function we have is y is equal to sine x quantity raised to the x. And in this case, x is restricted between 0 and pi. So we want to take this derivative or find the derivative, and what that means is we are going to take the log of both sides of this equation. So natural log of y equals natural log of sine x raised to the x. Now, what that's going to allow us to do is to bring this x down to in front of the logarithm. So we have the natural log of y equals x times the natural log of sine x. And then we take the derivative of both sides. The derivative of the natural log of y is 1 over y times dy dx. And that equals, well, we have to apply the product rule. So we're going to have the first times the derivative of the natural log of sine x, which means 1 over sine x. But then we have to take the derivative of sine x, which is cosine x. Then to finish off the product rule, it's plus the second function, which is log sine x, times the derivative of the first function, but the derivative of the first function is just 1. So therefore, we just have the log of sine x there. We can simplify this in two ways. One, we need to move the y over. So we'll have, dy dx equals y times the quantity x times, and we can combine these two to be cotangent x, plus the log, natural log of sine x. We should make a substitution here of y, because remember, up above, y is equal to sine x raised to the x. That will then give me the derivative dy dx as a function of just the variable x. So let's make that substitution. So I'm going to clean the screen, and we'll write out what that would be. Whoops. So dy dx will be equal to sine x raised to the x and times, in parentheses, x cotan x plus log of sine of x. And that gives us the derivative of y equals sine x quantity raised to the x. Well, now it's time for you to try a problem. And here it is for you. Use the technique of logarithmic differentiation to find dy dx. And the function you're going to be working with is y equals x raised to the log of x. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. Let's find out how you did with this problem. We have y equals the x raised to the log x, and we're going to take the natural log of both sides. So ln of y equals the natural log of x raised to the natural log of x. Now what we'll do is bring this down in front, and we have the natural log of y equals the natural log of x times the natural log of x. Now we'll do implicit differentiation. On this side, we have 1 over y dy dx equals 1 over, and we have to do the product rule here. So we would have the derivative of log x times log x, because both the first and second functions are the same. And over here, we'll have log x times 1 over x. We can combine those two together, of course, and get 2 log x over x. But in addition to that, we can multiply by the y. And so we'll have y times 2 natural log of x over x. And as we've done before, what we're going to want to do is make a substitution for y. We know that y is equal to x times the log of x. So we will get this answer. Y prime is equal to x to the natural log of x times 2 log x over x. Like that. And that would be the answer that you'd get for the pause video that you just worked on. All right, great. In this lesson, we explored exponential functions, logarithmic functions, and their derivatives. Make sure you work the exercises that your teacher assigns, and we'll see you next time.